So in this session, we'll learn basically 3 types of chi-square tests. So we'll start with the chi-square test of goodness of fit. Then we will learn chi-square test of association. Then we will see chi-square test for two proportion. So I'll be first taking a brief theoretical session. Then we will see the demo. Again, then second session and then third session. At the end of these 3 sessions, we will again have a breakout room where you have to practice each of these 3 separately. Okay, are the instructions clear? Am I making myself clear to all of you?
Yes, ma'am.
Okay, so with this chi-square test of goodness of fit. So as the name suggests, it tests how fit the data is. Again, we test this against a known standard or against a reference population. So in this session, first I'll be talking about the basic concepts of this chi-square goodness of fit. Then we'll see what are the research questions, what are the assumptions and hypotheses for this. So from now onwards, in all the tests, you will see these assumptions and hypotheses, because now we are testing for the these are the inferential statistics. In descriptive, you don't need to check for the assumptions, but in inferential statistics, because it runs on certain assumption, because you have to project the population parameter, that's why the assumptions checking is one of the very important tasks before you perform the test. Then we'll see the commands and interpretation, and then in the last, I will again summarize the commands. So the basic concept of this chi-square test of goodness of fit is, like it determines the distribution of case, but in this case, it is a single variable. So in a single, we don't usually what we do. Till now, we take 2 variables. You will see in the chi-square test of association also, you take 2 variables. But in goodness of fit, you take single variable. So you see the distribution of cases in the single variable, whether they follow a distribution or not. That distribution can be a known distribution. And if that proportion is not known, you assume it to be equal. And then again, if that hypothesized this thing, if the population is not known, then you hypothesize and you make it equal. If it is known, then it is never equal. So it is also known as the single sample non-parametric chi-square test, because it is a single sample. You are taking only one variable in this case, and it is known as the chi-square goodness of fit test. Like for example, if I did a study, maybe, and I want to compare it with the overall Indian scenario. And the status of India, I know that there are 5% children who are obese. And in my study, and that means that if I have 90 children, I may expect 18 cases of obesity because it is 5%. But there are 25 cases of obesity in my sample. And is this number is significantly higher than the expected or not? So the research question is, you want to know whether the proportion of BMI categories of MBBS students of your college differs from the national population. Maybe there's a national average, like how many proportion, what is the proportion of BMI, like medical graduates, how many of them are underweight, overweight, or maybe the normal category. Is your college standards are different from the national standards? Or whether if you want to compare, like if there is a ward and you have your own data of surgical site infection, and there's a hospital data also. So if you want to compare your ward surgical site infection rate with your institute or with your hospital surgical site infection rate, then also you can use this goodness of fit, chi-square goodness of fit test. Or if you know that your passing percentage, what is the college, passing percentage of the students, like in your college, 80% of the MBBS students, they pass. And if you want to compare it across any other college, like maybe AIMS Patna and IGIMS. So I want to say that there the percentage is 80%, mine it is only 60%. So if there is any significant difference between these two or not, or against some known standards. So for these thing, you will apply the chi-square goodness of fit test. So in this case, in all these research questions, what have you observed? That there is only single variable, and you want to test the proportion of various categories of a nominal variable in the against a known proportion or against a hypothesized proportion. So for that, the appropriate statistical test is the chi-square goodness of fit test, which is also known as the one sample chi-square test. Now there are basically three assumptions. The first assumption is there is only one categorical variable. This categorical variable can be a dichotomous, that means it has two categories like gender, male and female, or maybe cardiovascular disease, present or absent, or maybe students passing status, fail or pass, or it can be a polytomous. Maybe like if you want to compare the grades, like first grade, first division, second division, third division, or if you want to see the severity, mild, moderate, and severe. So if you have got more than two categories, we call those variables as polytomous variable. And then there should be independence of observations in such cases. What do we mean by independence of observation? Because in chi-square test and in case of a mean comparison of mean also, we will be talking about this independence of observation. So independence of observation means that if you have counted one individual in one variable, you are not going to count that individual in the another variable. Like if you have counted a person X under male, then you will not count that person maybe under the female. Obviously, we don't do that. But in case of paired observation, like when you do the paired sample t-test, you test the same individual for one variable, and then after some time you again test the same group of people. So those variables are known, those observations are known as the paired observation. In this case, the two arms of the categories, they have the different individual. That we mean by the independence of observation. And again, we emphasize that those two groups, they should not be related to each other. That means you will not take one husband in one group and wife in another group. You can do that, like if you have to take male and female, you can do like you can take 10 couples and you can take all male in under the male and all female under the female. But no, that will not be the independence of observation because they are related to each other. Similarly, if you take twins, and if you keep them separately in two groups, that is also not independence of observation because they are related to each other. So independence of observation means that the person, they should not, in the two groups should not be related in either way to each other. And the expected frequency of each cell, when you make a contingency table, so expected frequency should be at least 5 in each group. So the chi-square goodness of fit test, it compares the observed frequency in the categories with the hypothesized frequency. And we discussed that if the hypothesized frequency is known, you can put that, and if it is not known, then you take equal proportion. So again, this is same thing, hypothesized proportion is available, then you can quote that. And if it is not available, that you can say that it is of equal proportion. In this case, just to give an example, if you focus now on towards the left side. So I am showing you, please focus your attention right now for this case. So this is like you recruited 100 individual in your study and you want to know whether the proportion of normal, overweight and obese children is significantly different from hypothesized population or not. So you have got this hypothesized population as 50% normal, 40% overweight, and 10% obese. But if these values are not available with you, then what you can do, in the second example, you can see here that you can take this as a equal this thing. That means normal is 33%, overweight is 33%, and obese is also 33%. So if the hypothesized population is not available, the proportion, you can take them to be of equal proportion.
Why did we choose 33 here, ma'am?
100.
100.
We divide 100 divided by 3.
Okay.
Because there are 3 categories. If there are 4 categories, you will take 25 each. If there are 2 categories, you will take 50 each.
Yes, yes.
Depends on the number of levels actually. That's we learn na polytomous or binomial. If it is a binomial, 2 50 50 each. If more than 2, depending on the number of levels.
Okay.
I forget, and then Dr. Shamshad make me remember that I did not show these questions to you people. So this is the question, like you would like to understand whether the proportion of various disease severity of COVID cases admitted to your hospital follows the same proportion as those of national level. So in the national level, it is known that the 10% of the patients are of severe category, 20% are of moderate category, and 70% are either asymptomatic or mild. So we have clubbed these two, asymptomatic and mild, together. Now I have to use appropriate measure to check whether the observed frequency of disease severity, in this case, in my hospital, is it significantly different from the expected frequency of disease severity. So for that, what will I do? This is my data set. And this is the data for demonstration. So for this, you have to go to this analyze and all chi-square that is there in the frequency option. So go to, and before I move to that, I'll show you one more thing which I forgot yesterday. Maybe many of you know, can you see a plus sign here? So if you click this, all these modules you can install. Install module, and from the library you can install it. Again, yesterday I showed that there is a 3 dots here. So if you press these 3 dots, and if you press this syntax mode also, then you will see that all the commands, it appears like R. That we forgot to show you yesterday. So because these are not essential, that's why I'm unchecking this. But those of you who are interested in command learning also, you can see this. So now I have unchecked this. And this reference, maybe if you don't want this reference also, you can go here and then you can visible, you can make it hidden. So in that case, this reference will not be visible here. So now maybe I will just show you the goodness of it. So for that, go to the frequency. And then in here, you can see there are two options, 2 outcomes and n outcomes. So basically we click this n outcomes because in this case, you see that there are three proportions. So I will click this n outcomes. And then you can see here that there is a single variable here. So the single variable in my case, it was the COVID severity. So this severity, if I go down, this is the COVID severity, and I will move this variable to this row. Now, if you want expected count, you can click expected count. And in this case, you can see, in this case, if you don't mention, there is an option of expected proportion. If you don't mention, it takes automatically in a ratio of 1, this 33, 33, and 33. But I have a known proportion. So I'll again make it a ratio. So maybe asymptomatic mild is 70, moderate is 20, and severe is 10. So it will be in a ratio of 7:2:1. So then you can see the interpretation. Observed counts are 124 and expected is 126. Similarly, if I go down, you can see the observed count is 35 and expected is 36. So you can see there is a very less difference between observed and expected. Because if you remember the value of chi-square, how that formula calculates the value of chi-square. In numerator, you have observed minus expected difference ka square, and in denominator, you have expected. So that's why, if you remember this, then we know that this chi-square value, if the difference is less, then the value will not be significant. So in this case, you can see that in most of the cases, this difference is very less. That's why the value of chi-square is 0.56 with 2 degrees of freedom, because it is a 3 by, and then you can say that it is, the value is 0.756, which is not significant. So this is how we test that. Now what will be the interpretation? In the interpretation, you will write the underlying assumptions also. So underlying assumptions, you can say that the expected cell count. So in all the cases, you can see that the expected cell count is more than 5. It is not less than 5. So that assumption is met, and there is a single variable that is also there. So after that assumption, you can write that the difference in your hospital, the severity, although there was a slight difference from the national average, especially in the case of the severe, in your hospital observed was 21, national 10%. This, according to this, there was a no significant difference from the your data with the national average. That's how you can interpret the observation, whatever is coming to you. Again, going to the second question. So if I go to the second question again, the second demonstration is like, I would like to understand whether the proportion of male and female COVID cases reported in the district follows the same proportion as at the state level. Whether it is where it is known that the 40% are females and 60% are males. So now what will I do? Again, I'll go here. And instead of this, I will move gender here. So because there is only single variable. So I'll move this gender in this. And then you can see here in this case, you have to change the value. So female was 4 and male was 6. 60, 40. And then you can see that it is significant because the expected is observed is 50 and expected is 72. So there is a difference gross. I mean, you can see there is a difference between the observed and expected by 22. Here also you can see expected is 108, whereas the observed is 130. So this is the, we can say that this is significant and the value of chi-square is also 11.2. So this is how we calculate the chi-square goodness of fit. So is it clear to all of you? Then I'll move to the chi-square test of association. So once again, to reiterate, you have only a single variable and you test it against a known standard or a hypothesized one. If the known proportion is available, you can put these values in the expected proportion. If it is not available to you, then it will take these values as of equal proportion. Okay, and expected count, generally we don't report. We have only shown you the expected count just to know about the assumption, because in this case, we know that the expected count should be more than 5 and this is no more than 5. That's why, just to show you the difference. Otherwise, you report only the, what we say, the observed one. Is it clear to all of you?
Yes, ma'am. Ma'am, I had a small query here.
Yeah, please.
Yeah, ma'am. Somehow, if we have some values which are less than 5, then I read somewhere that we should use exact Fisher's exact test or something. So can we do that test out here in this?
No, but that option is there in the chi-square, not in the goodness of fit.
Oh,
here, if you see, there is no option of that Fisher exact. You are right. We will see that in the chi-square. In chi-square and the test of homogeneity, that means 2 proportion, you have got that option of Fisher exact, but not in the goodness of fit. Actually, what is there now? Here, it is not a 2 by 2 table. So if frequency is less than 5, then total sample size will be very less, because it has got only 2, 3, I mean, less number of, only one variable is there. That's why maybe that exact option, it is not valid for goodness of fit.
So if the value is coming less than 5, then we should not perform this.
You should increase, because then it will not be valid. Ultimately, you are projecting it to the population. That means your sample size is inadequate. You should increase your sample size. Or you can club the category. Like if you have 4 categories, in this case, it was mild, moderate, and severe. So the size is less, you can make it of 2 category only, where you can club maybe severe and non-severe. Then your problem of this less than 5 will be sorted out. Many a times we do that. If you have got many levels, then you should club the categories. That is one solution.
Okay. Thank you.
Yes, any other query? Okay.